This is lecture 1 for week 8 of CS 1030. And in this lecture segment, we're going to continue what we started looking at the end of last week, which is sort of some of the low-level stuff that goes on inside computers, and in particular, analog and digital representations. So let's return to this figure from the last lecture segment. So this is showing an analog computer signal, which varies, where voltage, the blue line depicts voltage, and is varying over time. So time is increasing from left to right on the graph. And the key thing here is that even though we have an analog computer signal, an analog voltage, the interpretation of these voltages is digital. So what we're going to do is recover the original digital signal by sampling the voltage at discrete times. So we're going to sample here and here and here, for example. We sample the voltage while it's not in transition, that is to say, while it's stable. And then when we look at a voltage, we consider anything that's below a threshold to be a 0, and any voltage above some certain threshold to be a 1. And the effect of this is that any detailed noise, any little bit of noise that's crept into the signal gets suppressed. What we should do, if we've designed everything correctly, is whatever the original signal that somebody tried to send to us from some other part of the chip or from some other part of a computer network, we should be able to exactly reconstruct the bits that were transmitted on the other side. And this is, again, the sort of the very key, this is the key ability that digital computers give us, is this ability to suppress noise and do lossless computations. And despite the fact that there is sort of at the very lowest level, there's no such thing as digital. At the very lowest level, digital computers is sort of a fiction that we tell ourselves. But at the slightly higher levels, once we sort of abstractly sample the voltage and we start treating voltages in a certain range as 0 or 1, then we can build this kind of illusion of a digital computer, and that's the thing that lets us make modern computers work at all. So when we represent analog data from the world in a digital fashion, we have to digitize it. And this digitizing is what we're going to talk about for this first lecture segment for this week. So what we do is we sample the analog data. So here on the right, we show an example of some sort of an analog signal. Maybe it's water pressure, maybe it's temperature. It doesn't really matter what it is. We can sample that data at discrete times. So if we're considering it to be temperature, for example, we might sample the temperature that a thermometer, some sort of electronic thermometer reads every 3 hours and round to the nearest degree. So we take a sample here, a sample here, a sample here, and then every sample is just going to end up being a number. So for example, here, it might be 85 degrees, and we represent that using the binary representation. Inside the computer, we represent that using the binary representation for 85. So we're going to end up making some sort of approximation here. If there are small variations in temperature during a 3-hour period, we're not going to catch it. So one question we can start to ask is, how good of an approximation of the real world are we going to capture using this method? And then also, how can we make the approximation better? And it turns out that making the approximation better is fairly straightforward. All we have to do is sample more frequently. So instead of sampling every 3 hours, we could sample every 1 hour or even every 10 minutes. And we can also make each sample better. So instead of rounding to the nearest degree, we could round maybe to the nearest 10th or 100th of each degree. And so there are these two basically completely separate ways of making a digital sampling of an analog signal better. We can sample more often, or we can make each sample better. So digitizing, that is to say, digitizing is taking an analog signal from the world and representing it in a computer, means taking a sample from an analog signal at regular time intervals. And the sampling part that's the sampling part. And then the other part of digitizing is quantization, which means taking in this infinite precision analog sample, that is to say, a continuously varying signal from the world, and rounding it to some fixed set of discrete numbers, which will then store in binary in a computer. Okay, so that's digitizing, and that's all we have for the first lecture segment for today.